Okay, this is videos for calculus, infinite series unit, and we're going to talk about two other tests. These are the last two tests, the ratio test and the root test. The ratio test, the reason why it's called the ratio test is it refers to taking a limit as n approaches infinity of the ratio of the next, so this is the next term in the series, and this is the current term in the series. So you're taking the ratio of two terms, one after the other, and it specifically has to be in this order. That's going to be the top and then the bottom. Okay, so the next term divided by the current term. All right, it turns out that this series converges absolutely when that limit is less than 1, and it diverges when it's greater than 1 or an infinity. Unfortunately, the test is conclusive when it's equal to 1. The ratio test is especially good if you have factorials, or you have things like this series that are expressed recursively, where the next term is written in terms of the first term. And actually, this ratio test is one of the most frequently used in the second part of the unit here. All right, let's do two examples of this. Let's say we have this series over here, number 1. If we're going to do the ratio test, we're going to just take the limit as n approaches infinity of the absolute value of the next term, so that is 2 to the n plus 1, changing all n's to n plus 1's, divided by the current term, right, which is 2 to the n over n factorial, the original rule as is. Now, normally I don't actually write that first step, because if you have a fraction divided by a fraction, it's the first fraction times the reciprocal of the second fraction. So usually I start this process this way. It's the n plus 1 terms rule, and then multiplied by the reciprocal, so it's the original rule upside down, a reciprocal of that. All right, so then we're going to do some factoring. On the side, let me show you something. If you have 2 to the n plus 1, you can write that as 2 to the n times 2 to the 1. Or just think of it as peeling 1 2 off, and you have 2 to the n left. The same thing with factorials. If I have, like, let's say 5 factorial, which is 5 times 4 times 3 times 2 times 1, I can peel off the 5, and then what's left is the rest of the factorial. So if I have an n plus 1 factorial, that's going to be n plus 1 times n factorial. All right, so we'll use those factoring techniques. Let me show you that. This 2 to the n plus 1 over here, we're going to write it as 2 times 2 to the n. And this n plus 1 factorial, we're going to write as n plus 1 times the rest of the factorial. Okay, and then I still have this. I'm going to make it one big fraction, n factorial 2 to the n, and we're taking the limit. Okay, so now there's cancellation that typically happens. So this 2 to the n cancels this 2 to the n. This n factorial cancels that, and we end up with limit as n approaches infinity of just 2 over n plus 1. The absolute value isn't really doing anything. If you have a constant divided by something that's going to infinity, that is 0. And because it's less than 1, you can say, therefore, the original series, n equals 1 to infinity of 2 to the n over n factorial, converges by the ratio test. So the good news is it's pretty straightforward. There's usually a lot of canceling that happens. It's perfect for when you have factorials. Okay, let's do another example here. Let me erase this. Okay, if we're going to do the ratio test here, then we're going to have to take the limit as n approaches infinity of the n plus 1 term over the n term. But since this is written recursively, if I just divide both sides by a to the n, that is just this ratio. So we're taking the limit as n approaches infinity of 5n plus 1 over 4n plus 3. And so that, because these are the first degree, both of them are the same degree, is just equal to 5/4. Because that's greater than 1, we can say this series, therefore this series, diverges by the ratio test. Okay, that's it. Now, if we happen to get 1, it just means we have to use something else. Example number 3 in the notes, if you're following along in the notes, is a case like that, where it then shows all the work to use other tests, which get really complicated. So we're actually not going to include it in the video. And if you want to take a look, this is a case that would, if you did the ratio test, would be 1, which is inconclusive, and then you have to use other methods. But for this video, I want to stay focused on the 2 tests. So that's the ratio test. The root test says something similar. We're going to take the limit as n approaches infinity, but it's going to be the nth root of the absolute value of the n. And if that is less than 1, the series converges, actually converges absolutely. And if it's greater than 1 or infinity, it diverges. And again, like the ratio test, it's inconclusive when this is equal to 1. Okay, let's see a couple of examples of that. So here, I can rewrite this. This is the same as n equals 1 to infinity of e squared to the n power, n to the n power, which means I could rewrite this as the sum n equals 1 to infinity of e squared over n to the n power. Okay, here is the power of the root test. If you can express your rule as the whole thing is raised to the nth power, the root test allows you to take the limit as n approaches infinity of the nth root of this. Technically, it's the absolute value. So I'm going to put the absolute value bars in there, but it's the nth root of this e squared over n to the n, right? And the nth root just cancels this off. Okay, the absolute value typically in these cases does not change anything, so you can safely ignore it. That means we're taking the limit as n approaches infinity of just e squared over n. The reason why I can ignore the absolute value is e squared is simply a constant and n is positive. Since I have a constant divided by something going to infinity, this is 0. That's less than 1, and therefore we can conclude that this series converges. E to the 2n over n to the n converges. Technically, you can even say converges absolutely by the root test. So the root test is really good when you have something where you have powers of n, and the whole rule can be written as something to the nth power. Here's another example over here. So we're going to do the root test over here. This means we're going to take the limit as n approaches infinity of the nth root of the absolute value of 2n n plus 1 to the nth power, which means that the nth power and the nth root are canceling, and we're taking the limit 2n over n plus 1. I'm omitting the absolute value because n is always positive. That is 2 because the degree is the same. It's greater than 1. Therefore, the series n equals 1 to infinity of 2n over n plus 1 to the nth power diverges by the root test. All right, so we saved the last 2, the kind of easier ones for the end. Some of these are harder, some of these are less difficult. If you want to see another example, you can do that. I'm not going to do it here. But let's quickly talk about the tests. So we've got some of them are based on the form, like the geometric series test, the telescoping series test, and the p-series test. They're depending on a form, right? Telescoping, usually you have to do partial fraction expansion first to get it in this form. But in geometric series, it's whether this common ratio is less than 1 that converges, greater than or equal to 1 diverges. And this is one of the rare ones we actually can find the sum. Telescoping series depends upon what happens at the end. You take the limit as n approaches infinity of that n stuff, and if it converges to a value, then the series converges, right? And you actually can also find the sum because you can add on the terms at the beginning. P-series is based on the form 1 over n to the p. So if that p is greater than 1, then it converges, and if it's 1 or less than 1, it diverges. So large values for p in the denominator converge because they make things smaller. Right? Geometric is common ratio less than 1, so small values in the top of the fraction here converge. Right? Then there's also the nth term test. You just take the rule itself. You actually can use that with absolute value as well. because of the theorem that says the absolute value converging means the series with the negatives will converge. But this can only be used to show divergence if this is anything other than 0. If it is 0, it doesn't show it converges. It means that you have to use a different test. Alternating series test. If you have an alternating series, if you have the limit as in the rule ignoring the sign is equal to 0, and it's a decreasing or non-increasing function for the generating rule, then the series converges. Alternating series tests cannot show divergence. The integral test says if you have continuous positive and decreasing function that represents that, so there's conditions that have to be shown, then if the integral from 1 to infinity converges, the series converges. If the integral diverges, this diverges. Right? We have the root and the ratio test that we just used. Those are for specific forms when you have a rule that has to the nth power. Or you can try the ratio of the next term to the current term. Less than 1 converges, greater than 1 or infinity diverges, inconclusive at 1. And then the direct comparison and limit comparison. In limit comparison, you're comparing the ratio of two different series. And if they are a finite positive number, the series are linked. So if the similar series converges, the original series converges. If it diverges, diverges. And direct comparison depends on the direction being correct, whether the new series is converging on the right and squeezing the original one on the left down, or diverging on the left and pushing the one on the right up to diverge. And that's it. That's the list of all of the series. All right.